So today we're going to talk about one of my favorite subjects, the Mandelbrot set. Okay, so most of the research that I'm doing actually started from my research into fractals and the Mandelbrot set. My interest in complex numbers and quaternions also stems from my interest in the Mandelbrot set. Now, historically, we've used complex numbers to generate the Mandelbrot set. And so complex numbers have two components, or two tuples, as Hamilton calls them. The complex numbers are two tupled, and therefore the Mandelbrot set is a two-dimensional image. So we are converting the tuples to dimensions when generating the Mandelbrot set. This is the A dimension, or the real dimension, and this is the B dimension, or the imaginary dimension. And so historically, this is how the Mandelbrot set was generated, and historically, the Mandelbrot set is a two-dimensional image. But today what we're going to do is we're going to apply quaternions to the Mandelbrot set. And we are going to be using the 4x4 matrix version of quaternions to generate a four-dimensional Mandelbrot set. Now, visualizing a two-dimensional Mandelbrot set is quite easy because computer screens are two-dimensional, pieces of paper are two-dimensional, and so it is quite easy to visualize a two-dimensional image on a computer screen. Now, visualizing three- and four-dimensional images is a little bit more complicated, and this is why it is difficult to generate and render a four-dimensional Mandelbrot set. Now, there is no such thing as a three-dimensional Mandelbrot set. People have been searching for it for years and years, and they can't find it because there is no such thing. And there is no such thing because there is no concept of a three-dimensional complex number. Okay, so there's no such thing as a three-dimensional complex number. There are two-dimensional complex numbers, and there are four-dimensional complex numbers, which we refer to as quaternions. Now, the reason I like the 4x4 matrix version of quaternions is because it makes it quite trivial to implement the Mandelbrot set using the function z equals z squared plus c. Okay, so when we use complex numbers to generate the Mandelbrot set, z and c are both complex numbers. Okay, so when we use quaternions to generate the Mandelbrot set, z and c are quaternions. Okay, so this is what we're going to do today in this generation of a four-dimensional Mandelbrot set. Z and c are going to be 4x4 matrices. They're going to be the special 4x4 matrices that we call quaternions. So these are the 4x4 matrix implementation of quaternions. We'll be using that to generate a four-dimensional Mandelbrot set. But first, let's do just a quick review of quaternions and the 4x4 matrix implementation of quaternions. Okay, so quaternions are, as I said, four-dimensional complex numbers. They have four components, or what we call four tuples, what Hamilton called four tuples. Okay, so they're not necessarily four-dimensional. I don't really like to refer to these as dimensions. However, in the generation of the Mandelbrot set, we are in fact using each tuple as a dimension. So this is why we are able to generate a four-dimensional Mandelbrot set. So here we have the algebraic form of the quaternion. This is A plus BI plus CJ plus DK. Okay, so you'll notice that I have a little 1 in here. So technically A is the real component, what we call the real component, and B, C, and D are the so-called imaginary components. Okay, so the real component, so I put the 1 in there because I believe it belongs there. And you'll also notice that I put square brackets around the 1 and the I and the J and the K. And this is my notation, okay? I do this specifically because when I am using the 4x4 matrix version of Quaternions, okay, so here I have the 4x4 matrix of the Quaternion, of the A component, the B component, the C component, and the D component, and where they belong in the 4x4 matrix. So when I write the units in square brackets, so this is the unit of the real number, this is the unit of the imaginary I component, the imaginary J component, and imaginary K component, and I put them in square brackets. So that is my notation. Okay, here is the 4x4 matrix, generalized 4x4 matrix that we're going to be using to generate the Mandelbrot set. And here is the code that I use. So when I want to set up a 4x4 matrix, I have a function, and this is the code that I use. And I like to write my code in such a way that I can see the matrix. I can see the matrix in the code. So that way I can check for bugs, because 4x4 matrices are, kind of ugly. Well, I actually think they're beautiful, but other people might think they're ugly just because maybe they don't look nice in a paper. And so this obviously would look much nicer in the paper. But under the hood of this, it is my opinion, there is a 4x4 matrix that looks like this. And this is in fact what the Quaternion looks like under the hood. Now, a lot of people have complained to me about the 4x4 matrix implementation of Quaternions, especially when it comes to Quaternion operations, Quaternion multiplication and addition, because when we're trying to transform a vector, a point, okay, which people refer to as vectors, when you're trying to transform a coordinate from using a Quaternion, to do Quaternion rotations, technically I'm doing too many operations, okay? So when you multiply two matrices together and you just multiply them straight up, you are doing 4 times more multiplications and 4 times more additions than is actually necessary to get the job done. And I agree with that. In principle, I agree with that is in fact a problem. So when I went about to program the Mandelbrot set using the 4x4 matrix, I modified the computer code to be more efficient. Okay, so when in the previous examples that I've shown you in previous videos, I was using my matrix multiplication. I was just doing 4x4 matrices. I was doing 2 for loops. Okay, I was doing it, integrating through both matrices, and then I was doing the multiplications and additions right here. And so when I was using this method, it definitely was extremely inefficient. I was doing 4 times more calculations than I needed to do to get the job done. And so under the hood of this for next loop, or this for loop, I wrote a brute force method. Okay, so this method here, I am doing all of the 64 calculations, or I'm doing all of the calculations for the matrix. So this is multiplying the 2 4x4 matrices together, and this is doing it outside of the for loop. So this is what the for loop is doing. Under the hood, it's doing this, and this is still way too many calculations for, it's not efficient at all, but it does get the job done. Okay, so I liked it. It got the job done. It made my the implementation of these matrices quite simple in the front end. So in my application, it made the application simpler and easier to manage. And then under the hood, we had this. And so what I did, so using the fact, let me go back. So using the fact that Quaternions are 4 tuples, so there's only 4 unique values in the matrix. right? There's only 4 instead of 16. So it's not like a 4 by 4 matrix where every value in the matrix is different. Okay, so this is 4 tuples. There are only 4 unique values in the 4 by 4 matrix. So all I really need to do is calculate the A tuple, the B tuple, the C tuple, and the D tuple. I need to calculate those values. Okay, that's all I need to do is calculate the A, B, C, D, and then put them back into the matrix in the correct location. Again, I'm writing in my code, I'm writing the matrix in the familiar form that looks like this matrix. So if you look at this matrix here and you look at my code, you're going to see the same pattern. And so again, I do this for debugging so that I can see whether there's any bugs, if I forgot to put a negative sign here or something. It's just easier for me to manage. And so this implementation of matrix multiplication for the 4 by 4 quaternion matrices is much, much more efficient than this method or this method. Okay, so using 4 next loops is actually hugely inefficient. It tends to be worse than the brute force method, but because of the redundancy of the tuples in the quaternion matrix, I'm able to simplify it and get much closer to the, say, algebraic implementation of quaternion multiplication. And this is really important for the Mandelbrot set, because in the Mandelbrot set I'm doing thousands upon thousands of iterations. So for each pixel I'm doing many, many, many more multiplications than I would be doing for, say, a rotation. So if I want to rotate a point about an origin, about an axis, I really only need to do 1 multiplication. But let's say in the Mandelbrot set, if I'm doing 100 iterations, that's doing 100 multiplications and 100 additions. And so I also applied the same technique to the addition operator. So my quaternion addition is just calculating the A, B, C, D, and then filling in the matrix. And so both the multiplication and the addition are much more efficient than I had previously implemented in, say, the code that I gave you guys for the rotation, for the quaternion rotation applications that I posted on my in my YouTube channel. So here is the code for my Mandelbrot quaternion generator. Okay, so I'm using my code base from work to do this, because in my code base from work I have a wonderful way of visualizing three-dimensional volumes, volumetric data. Okay, so I've shown you this before in some of my other videos. This is a cube, basically a cube that you can slice into and slice and dice, and you can look volumetrically inside a volume of data. And so this is what we're going to use to generate the Mandelbrot set. Now this is only a 3-dimensional visualizer. It is not a 4-dimensional visualizer. We can only look at 3 dimensions at a time. Okay, so I'm going to show you, so because the Mandelbrot set is 4-tupled, so here are the 4 tuples. What I'm doing is I'm integrating through the 4 tuples, okay, the real, the I, the J, and the K tuples, or the A, the B, the C, the D. So A and R are linked, B and I are linked, C and J are linked, D and K are linked. That's why I named them like this. So these are the 4 dimensions of the Mandelbrot set that we're going to be generating. And so, but obviously we can't visualize 4 dimensions. So what I'm going to show you is I'm going to generate a 4-dimensional volume. Okay, this is going to take a bit of time to generate. It takes, actually not that bad. I'm doing like 200 by 200 by 200 by 200, and it takes about 30 seconds to generate. So it's actually with my more efficient multiplication and addition operators. And so it's actually not that bad, but it's low resolution. It's very difficult to go to high resolution because it's 4 dimensions. So I need 200 times 200 times 200 times 200, and I'm generating a 4-dimensional volume. So now what I'm going to do is I'm going to generate the Mandelbrot set for each quaternion point in the four-dimensional volume that I am going to generate. Okay, so first I have to calculate the, for each, call it pixel, we call it a voxel. I don't know what it's called in 4D. In 3D we call them voxels. In 4D, I guess we can still call them voxels. And so for each voxel in my 4D volume, I need to calculate the location in space, in that space. And so I calculate the real, the imaginary, the I imaginary, the J imaginary, and the K imaginary component. And then I set them up into the 4x4 matrix. So my setup quaternion in my code looks like this, right? So my setup quaternion function in my code looks like this. So I pass in, let's see, I pass in the A, B, C, and D, and I store that into the matrix. And so here I'm putting the A's, the B's, the C's, and the D's into the correct location in the quaternion 4x4 matrix. So that is basically what these functions do. And so I've got a matrix called that I call Z, Z-E-D, and I have a matrix called seed, which is C. So this is Z equals Z squared plus seed. And I use the word seed for fun because, well, because C sounds like seed. I have a little bit of a list so that they might sound the same to you. They sound the same to me, C and seed. So I put, you know, my matrix Z and my matrix seed. I set them up to the initial value, these values here. And I do this, now historically, they always set the initial value, the initial Z to 0. But when you do the first iteration, it turns Z into the C, into the original seed. So basically I set the Z to this, and I set the seed to this, and this takes care of the first iteration. Okay, so once we're set up, then we have to go into the iteration loop. So this is the iteration loop. This is a while loop. So I'm going to iterate until the point either escapes or it reaches max iteration. So it didn't escape in a certain amount of time. Okay, so now all I need to do, this is so simple. I've got 2 lines of code here to do the iteration. Okay, so I take the Z matrix and I multiply it by the Z matrix in the efficient way that I showed you. And then I store that into a temporary matrix. Okay, so then I take that temporary matrix and I add, so then I do add quaternion, so I use the efficient add quaternion to add the seed, and then I put it back into Z for the next iteration. Okay, so when you do it algebraically, the code is a little bit more convoluted. When you do it algebraically, it doesn't look anything like Z equals Z squared plus C. Okay, it looks different. It looks, you do not see the Z equals Z squared plus C in the code itself. Okay, so when you do it algebraically, you have to break everything down into algebraic form, and then you have to do the iteration process on that. So basically, the multiplication of 2 matrices under the hood actually does the algebra for you. So the algebra is still being done. It's still exactly the same. There's no difference. Only the algebra is being done for you. The FOIL rule, remember the FOIL rule? We multiply two vectors together. It is actually, that is what is going on under the hood when you multiply 2 matrices together. That is why I like the matrix form of quaternions, because it actually does the algebra for you. So if you don't like algebra, if you think algebra is hard to understand because of the symbolic language of algebra, which I find very difficult, if you actually want to understand quaternions without having to worry about those details, then this is a good way to go. Okay, so, and because I have made the multiplication and addition much more efficient, closer to what you would get if you used if you did these things algebraically, then you are not losing anything, but you're gaining something in terms of an intuition about what these Quaternion, these 4x4 matrix Quaternions are. This is a Quaternion. Okay, this is a Quaternion. This is the algebraic form of this, and under the hood, this is the most transparent implementation of Quaternions that that exists, in my opinion. I like it, I understand it, it's intuitive. You don't have the complication of the hypergeometry and trying to understand Quaternions because they're four-dimensional. Yeah, in the Mandelbrot set, the 4D Mandelbrot set, I am implementing the Mandelbrot set as a four-dimensional object. Okay, but Quaternions themselves are not four-dimensional. They're only four-dimensional when you want to plot them as 4 dimensions. Okay, Quaternions are basically 4x4 matrices. So they're 4 tuples. They're not 4 dimensions. So calling Quaternions 4-dimensional is a little misleading. Yes, I'm using them 4-dimensional as 4-dimensional objects in this implementation, but in general, Quaternions are not 4-dimensional. They are 4 tuples. 1, 2, 3, 4. And I think it's really, really important to understand this, to really, truly understand Quaternions to the root of what they are, which are 4x4 matrices. Okay, so back to the code. So we do our multiplication, we do z squared, and then we do plus c. Okay, then we copy the values out. So the return value of the Quaternion is the top row here. So I am using row convention, and so when I multiply 2 matrices together, I want to get the point. I want to get the tuple back out of it. Okay, I use the top row right here, and that is what I'm doing in my code. Okay, so I am using row column convention. So I'm pulling the first row out of the matrix, and that is going to be the value that I test. Okay, so the next thing we need to do is we need to calculate the distance. So I'm doing a distance calculation, which is the square root of the first value squared plus the second value squared plus the third value squared plus the fourth value squared. You get a distance calculation, and just like in the Mandelbrot set, if that distance is greater than 2, then we are escaping. Then we are escaping the Mandelbrot set. We're going to say escape is true. But if we get through all the iterations, if we iterate and we go past the max iterations, then I'm going to stop my while loop and I'm going to say escape equals false. So then basically I'm done. So if the value escapes and we have more than 0 iterations, then I calculate the index of the 4-dimensional matrix. I calculate the index of the 4-dimensional matrix, and I create a value. Now my 4-dimensional volume is a grayscale volume. It's not a color volume. If it was a color volume, it would be 3 times bigger than the 8-bit volume that I created. And then I'm going to start running out of memory in my computer. And so I just do this in grayscale. The visualizer that I use for this works in grayscale basically because it is used for ultrasound images and MRI images, which are for the most part usually grayscale images. And so I calculate the index, I calculate the value based on the number of iterations, and then I put that value into the buffer. Okay, so that's the hard part. Now when this is complete, I now have a 4-dimensional buffer to extract my 3-dimensional image from. And so that is what I'm doing down here. Okay, so down here, what I'm doing is I'm just taking from the 4-dimensional buffer, I'm going to create 2 volumes of data. One volume of data is going to have the real the I and the J component of the four-dimensional matrix, and the second volume is going to have the I, J, and K. Okay, so the volume on the left is going to contain the real component and two of the imaginary components, and the volume on the right is going to be purely imaginary, I guess you can call it that. It's going to have no real component involved, and we're going to be looking at I, J, and K, 3D volume that contains only I, J, and K. Okay, so after running the code, I end up with these two volumes. Okay, I end up with these two volumes. You can see this is volumetric data. Okay, so you can see I can slice through the volume. I can look at it from different directions with this visualizer. Now, this is the visualizer that my team and I developed many, many years ago in 1993 when 3D ultrasound was just starting out, and we developed our own technique for visualizing this way, and we patented it and licensed it out to a bunch of companies. And so this has been around for quite a number of years, and I have been using it. I use it at work for 3D ultrasound, or for 3D MRI, or for 3D CT visualization of volumetric data. Okay, so this is where I can look inside the volume, and I can investigate different regions of the image. So this is the image that has the real and the two imaginary components. Okay, and you can see the Mandelbrot set in this image. Okay, so there's the Mandelbrot set. It's low resolution because my image is only 200 by 200, and I only did 5 iterations. So this is the first iteration, this is the second iteration, this is the third iteration, the fourth, and the fifth. So it gets brighter as it gets close to this edge here. And so each time I do an iteration, this boundary gets closer and closer and closer to the idealized Mandelbrot set. And so this took about 30 seconds to generate, doing 5 iterations. So you can imagine if I wanted to do 100 iterations, it would take quite some time to generate this image. Okay, so this is the real component, is this vertical here. Actually, what I'm going to do is I'm going to do a reset. I know that most people are used to seeing the Mandelbrot set displayed like this, where this is pointing to the left. And so this is the real component. This is the A component of the tuple. So this is the A tuple in this direction, and this is the B tuple in this direction. So this is the A, B plane. This is the complex plane. Okay. So this is the original complex plane. This is X, this is Y, this is real, this is an imaginary, and this is the standard way that the Mandelbrot set is generated. And so, what you will see is now when I look at it this way. Okay, this is the. Let me get right to the middle. Okay, so now this is the A tuple. This is the C, ABC. So this is the C tuple, and you'll notice that A and C is also a complex plane. And although it's not in this volume here, A and D obviously would be a complex plane. And interestingly, when I say go in, I try to slice in by 45 degrees, it's still the Mandelbrot set. Okay, so it's still the complex plane. So even an oblique slice through this volume is going to be a complex plane. And so you can see that when I go in this direction, you see that it's got circular symmetry all the way through. And so no matter what plane I pick as I slice through the origin is going to look like the Mandelbrot set is going to be a complex plane. Okay, and complex planes are two-dimensional, and this is a two-dimensional slice, so that kind of makes sense. So on the right here, what we have is the pure imaginary. We have the pure imaginary, so there's no real component in this. So we're looking at the I, J, and K volume. Okay, and you'll see that this has just spherical geometry. Okay, so there's no fractal, there's no Mandelbrot. Basically, it is just a sphere. Let's zoom in on this a bit and shift it over. Okay, you can see that this is purely a spherical geometry. And so this is like this is IJ and this is IK. Okay, so this is IJ, IJ, and this is IK. So, so the three IJ and K are built into this, and you end up with a spherical geometry. And so this is what the Mandelbrot set looks like in 4 dimensions when I ignore the real component, when I don't plot the real component. Now I'm not setting the real component to 0. Okay, so I'm not setting the real, when you set the real component to 0, if you tried to generate the Mandelbrot set, you definitely would not get a fractal. The real component is the important part here. If you want to generate a fractal, you can't ignore the real component, right? We have, here we have only the imaginary component. We're only looking at the 3 imaginary components. And here we're looking at the real component and 2 of the imaginary components. And so if we look at these 2, when you look at this one from, say, the bottom, okay, you get the same image that we get over here. And so you can see that when we only look at the imaginary components, you only get this circular or spherical geometry. Okay, so whether this means anything or not, I don't know. Whether it means anything in terms of physics, I don't know. But I think this is really interesting. And so let's, I want to reset this back. And so I actually like the Mandelbrot set displayed vertical like this. This is still the real component. This is still the imaginary component. Doesn't really matter how you orient it or display it. Okay, it is still the Mandelbrot set. So one thing I did notice when looking at these 2 volumes side by side is how much it reminded me of the figure that I had from my paper, the Mandelbrot set as a quasi-black hole. Now I wrote this paper long before I ever did this Quaternion implementation of the Mandelbrot set, and so in the paper, Mandelbrot set as a quasi-black hole, I'm comparing the Mandelbrot set to the Schwarzschild black hole, the geometry of the Schwarzschild black hole. And so I was a little bit surprised myself when I implemented this and I put these 2 side by side, and I noticed that that I had actually inadvertently recreated this figure that I had from my paper. And so, of course, I've often wondered whether there was some connection between the Mandelbrot set and the cosmological black holes, and this kind of gives me another clue to look at that possibility. Now, the fractal nature of the universe, I believe the universe is a fractal, and in fact the universe does look a lot like the fractal. So this is a figure from my paper. On the left we have a region of the Mandelbrot set, which I describe in figure 7, and on the right is a galaxy where the geometry of the galaxy is very reminiscent of the geometry that you see here. Although the geometry of the Mandelbrot set is a little more contrived, I guess, is a little more perfect than the geometry of the galaxy. You can see that the spiral patterns are very similar, and here you have sort of a larger kind of extended part kind of coming off the end of this arm here, and we have similar things going on here. And so the similarity, the self-similarity, is very intriguing in my opinion. And so this is something that I'm going to investigate further. It is possible that one idea I'm entertaining is that that the imaginary components of the four-dimensional Mandelbrot set might possibly represent the spherical geometry that we see in real life, and that the real component is actually the component that we can't see. So other people that I've talked about on this channel in the previous presentation I gave on a paper where the author of the paper was talking about the imaginary components of the Quaternion being pointing in directions that we can't see. And I think it's actually quite possible that it is the real dimension that is pointing in a direction that we can't see, and that the three imaginary components are actually correspond to the Cartesian coordinate system that we can see. And so this is just an idea that I'm entertaining, and so it's something that we can look at to maybe further the investigation into the fractal nature of the universe. So that's all I'm going to say for now. I just wanted to get this out there. I've been wanting to make this video for a long time, and you know, I've been fine-tuning my code to make it easier for me to understand and for hopefully other people to understand. And so I'm going to leave it at that, and well, I'll be back.